Hello everyone, welcome to my YouTube channel. I'm finally back. I think it's been a few months already since my last video. I was very busy. This last year, 2025, was a crazy year. A lot of happened in my life, and I think I was just busy living. I'm still in Germany. I'm still working in an EY company. I'm still an engineer, and I'm very happy to be finally here, to be finally back. And in today's video, I really wanted to share with you something different than computers or something like that. As you probably already remember, I finished my PhD. I finished on 2024 December, so a little bit more than 1 year ago. And I'm super happy because of that. A lot of things changed as well, and I got a lot of free time. And that's why probably I got not anymore into my YouTube channel this last year because I was just out there trying new stuff. And yeah, but I had the opportunity to record myself when I was doing my PhD defense, and it was actually pretty funny. I was doing, as you remember, probably my PhD in Barcelona. So it was in the University Polytechnic of Catalonia. And I recorded the whole video of my PhD defense. It is a very long video. That's why you probably are watching now this very long video. But I just wanted to share it because probably a lot of you engineers out there, or a lot of you young students that are out there, probably you have as well interest on pursuing maybe like a master's degree or maybe as well a PhD on engineering. Myself, I was in computational mechanics, in structural mechanics and biomechanics. And maybe you are as well interested on something like that, maybe going to the level of holding a PhD degree. So maybe this is interesting for a lot of you guys out there doing simulations, doing stuff incredible with computers, with high performance computers. And I was this probably made very interesting because, for example, myself, when I was doing a lot of research, how to prepare myself for my PhD, I really did not found that much information in YouTube, or maybe just a few guys out there in YouTube that actually explain how they actually PhD defense went and everything. And I was like, yeah, okay, maybe it is actually helpful to see how actually a PhD defense goes. I know there are some universities that post them online especially, but I don't know. I just want to share mine with you, and I had the opportunity to record it. So I hope you like it. I did my best to add subtitles to the whole presentation time. I think it's like 55 minutes, like almost 1 hour of presentation myself, and like 1.5 hours of questions and answers of the committee and supervisors and everything. So it's a very long video, but the most important and interesting, I think, is the first hour. And I did my best adding subtitles. And I correct all the subtitles to match almost as good as possible as I was trying to really inform. So it should be actually quite accurate because I went to check everything. So I just hope you like it as well. Maybe you don't see it, maybe it's too much, but maybe if you are looking for some information, how my PhD defense was and how maybe you can prepare for yours, maybe this is helpful. So this is also as well, this happened in Barcelona in 13th of December of 2024. So yeah, it took me quite a long time to prepare this video, but now I'm finally happy, and I just want to share this with you. So thank you guys as well for being back here, and please enjoy the video.
Okay, good morning everybody. Buenos días todos. Sorry, I can't speak Catalan. Puedo hablar español, pero catalán no tengo ni idea. It's a pleasure for me to introduce the committee. So my name is Richie Gill. I'm Professor of Healthcare Engineering at the University of Bath. And joining the committee is Jerome Noali, sounds that okay, and Xavier Delfort. And we are here to do the defense of Jorge. So Jorge, you're going to present to us for about 45 minutes?
Between 45 minutes and 55 minutes,
yeah,
more or less.
Okay.
Yeah.
And then just so that you know the process, after that you've done your presentation, we will have a series of questions, and then they go opportunity to ask some questions. After that has finished, there'll be an opportunity for the members of the audience to ask you a question if they have any. And then after that, we will have a discussion with the committee without everybody else present. And when we've made a decision, we'll bring you back in and tell us what you got for the lunch. So, over to you, Jorge, and what's your presentation?
Thank you very much. So let's jump straight into it. Today we're going to talk about the modeling of orthopedic surgeries using advanced biomechanical computational techniques. So this was a long journey, already 36 months approximately, and it was several clinicals and other institutions take part as well onto these projects, series of projects, and from Mexico, here from Spain, and after we're going to take a look at them. But just want to let you know the research environment was a little bit, a lot of people take part in it. We're going to start with the introduction. Osteoarthritis. I think all of you probably already know the burden of osteoarthritis and how it really impacts the humans nowadays. Approximately 44.7% of the pain experienced by adults or humans are caused by a kind of osteoarthritis, and in specialty knee osteoarthritis and rheumatoid arthritis. And as you can see here, KUA affects approximately more than 250 million people worldwide. So what I want to find in this is that this is actually something to take care about. It's something to think about it because it affects actually people. The knee osteoarthritis is caused by many factors, but one of them is the degeneration of the articular cartilage. And this occurs as a result of wear, tear, by age, by mobility, maybe inflammation, maybe injuries that you have in your life, and mechanical stress, of course, as well. For example, like obesity, in which the knee joint is really stressed. And medial compartment is one of the most commonly affected in the humans. As you can see here as well, with the degeneration of articular cartilage, there's one point in which the medial compartment tends to slip against each other, forms caries, and then it affects at the end into pain or inflammation or just dysfunction of the knee. There's a lot of treatments to solve this, and usually they tend to end in surgical interventions. There are as well non-surgical interventions like non-pharmacological, that you can lose weight, maybe you can do some exercise, you can get some therapy diagnosed, maybe as well pharmacological, like to reduce pain, maybe injections, and the surgical treatments, one of the most common as well, is total knee arthroplasty. It's one of the typical methods used to restore the knee function, and it consists usually into literally remove one part of the joint that is affected by this degeneration and replace it with some implants in order to restore the function of the knee. And there is another one, which is called high tibial osteotomy. And this is one of the most common as well surgical intervention in order to treat the knee osteoarthritis. And for usually medial compartment early stage osteoarthritis. And it usually incorporates the use of implants, probably metal, and they are going to correct, and they are going to fix the bones or the mechanical system as well into an alignment in the joint, and then they are going to correct the malalignment. There are also emerging solutions for this phenomenon, and there is one which is called proximal fibular osteotomy, which if we have a leg system in which it's a normal, healthy leg system, and then we have a system which is affected by osteoarthritis. Probably we have deflection, we have malalignment, and we already spoke about it, and what this causes is probably, as we use, the degeneration of the medial cartilage most of the times, but as well the joint space is going to be narrower and narrower, and we have, of course, when we speak about the mechanical system, we have a distortion a disruption in the mechanical system. And this proximal fibular osteotomy states that if you remove a part of the fibular bone, you can put into place, or you can set as again the mechanical system, the joint system, and the loads are going to balance as well. So it states that fibular support is a potential contributor for the deviation of the tibial plateau. And when you preset the fibular bond, you actually generate a shift in the mechanical axis of the system. And with this, you can improve the weight bearing or the load distribution in the knee joint. Why is this important? Because in some places or in some countries, as developing countries, maybe there is not always the chance to pay for implants, or maybe there is no the personal or the expertise enough to do some of these other surgeries that we just talked about, like DKA or HTO. And of course, low-income patients. Not everyone can as well pay for that heat treatment. And maybe this PFO can act as a solution for those people. The background of PFO, it starts around 2013, in which some scientists started to check in cadavers, in cadaveric studies, that when you actually resect the fibular bone, you have a change in loads. It was just like a some study. They didn't intend actually to use it as a treatment for osteoarthritis, but they started to see, hey, when we resect fibular bone, something happens. And in 2015, in China, they actually started to use partial fibulectomy in order to treat patients with medial compartment osteoarthritis, which was the first point in theory in which people started to use this as a solution for arthritis disease. And it was later in 2017 where some clinical studies started to happen, and we have, for example, a study here from one et al. That 47 patients were treated with proximal fibular osteotomy, and they immediately had pain relief, improved walking, improved function, that I say, and increased as well the knee joint space. It was narrow and it increased just like suddenly increased, if you can say that. And in 8 of the 47 patients, there was actually a correction of the malalignment, of the deviation of the mechanical system. So at the end, they conclude that PFO may really relieves actually pain and improves the joint function. So it was in 2017. After this, and more that in the direction of the topic of today, is that of course people started to as well to analyze this in a digital way, not always in clinical trials or in vitro trials. So they started to analyze as well what was the stress concentration, the force applied, the force distribution applied in the area of knee joint when using actually proximal fibular osteotomy. And they started by analyzing the effects before PFO and after PFO. And they started to notice, well, yeah, it is true. There are changes. Something is happening there in the tibial plateau when we analyze the knee joint. And as well in 2020 came out as well one study that they started to dig deeper into the topic that something is actually happening in the knee joint. The thing is that they left actually a research gap there. And there was a starting point of this work actually, in which why it happens, how actually PFO works, because they started to make some statements, they started to analyze it, but no one really went to explain what is actually happening in the mechanical system. So there are two main theories that actually they were stated that may explain what is happening. One of them is the theory of the non-uniform settlement. It was stated by Tong in 2015. And the other one is the theory of the two many processes. And we're going to retake these theories at the end of the presentation. So for now, I'm just going to give a very brief explanation on what more related states. So the non-uniform settlement states that with the time aging, as we grow old and we get as an adult, the medial compartment or the knee wants or tends to settle down. And because of the support provided by fibula, the lateral compartment is allowed to settle down. And with time, it as well, of course, tends to take the loads to the medial compartment. And the theory of the two many cortices states that we have three cortices systems. So we have a system in which the fibula is an extra cortex that is actually as well not allowing the knee joint to settle, to load, to properly balance the loads into the knee joint as we provoked. For all of you, as an interesting introduction to the PhD, Prakash in 2016 published this study about the two many-cortices, but Dr. Prakash was, actually this topic came about in 2003, because he was in a prison in India. And they started to notice how inmates were actually getting better by leg problems that they had because the fibula bone was broken, because of injuries that they were provoked or they got injuries. Patients actually got better by doing this. And Dr. Prakash was not actually the doctor, the prison doctor, he was an inmate as well. And he was an inmate as well, so he practiced, he helped his inmates, colleagues, and doing this. So this is how a little bit started in 2015. That's pretty interesting, to be honest. And that's how we go into the topic of simulation and in silico modeling. And the problem with PFO is that you cannot tell everyone you are going to get better if we get you one broken. It's the acceptance, the widespread acceptance of this surgery. It is still very ambiguous. It's still very ambiguous, and there is not that much biomechanical evidence to support what is actually happening and how it works. So we are just not enough biomechanical evidence to push this forward for the medical community. Everyone says that it works, there are studies that it works, but no one can really tell you how exactly it works. So, as well, we saw this research out. And with in silico modeling, it's pretty nice, there's a lot of advantages, but there is as well some challenges. Everyone states that simulations may accelerate innovation of medical implants, of medical treatments, procedures, but of course, innovation comes with challenges. And for these challenges, you need improved processes, you need better guidelines, you need better understandings to how actually you can perform in silico modeling in a better way. So we came out with three main research questions. The first one is, what are the differences in mechanical behavior, stress distribution, and knee joint contact pressure between HTO and PFO to assess its clinical implementation? We say, okay, let's take something that is already there, well studied, well performed, practiced, and well, let's use it as a reference in order to assess the clinical effectiveness of PFO if we can. And then the second question is, what is the influence of varus valgus anatomical misalignments of a patient lower extremity in effects of PFO? There are, of course, natural variability from each patient, and this may affect, of course, the effectiveness of PFO. And how these initial conditions or specific conditions can be related to trend in change of stress distribution and center of pressure of the region. There's a third question that is a little more general, which is if PFO is actually feasible to restore knee joint dynamics. And of course, how can we conduct studies on this procedure without risking or compromising patient safety, which is one of the main problems as well. So we define a few objectives. Investigate, describe, and analyze the biomechanical effects of PFO as a treatment for in osteoarthritis. Propose the biomechanical PFO, propose a biomechanical in silico PFO model, and we want as well to quantify the dynamics effects of PFO on an athletic knee joint depending on the patient-specific data and in a controlled in silico manner. We divide this work into 5 main chapters we are going to talk about today. In chapter 3, we are going to take a look to a systematic approach that we developed in order to ensure standardization of our own studies presented on this work. Chapter 4, we are going to take a look on the stress distribution and contact pressure before and after performing an in silico PFO. In chapter 5, we are going to take a look and dig deeper into the material parameters of secondary anatomical structure of the knee joint in order to maybe improve the modeling and accuracy of the in silico models of the knee joint. And in chapter 6, we took a look to the influence of the varus valgus effects over the PFO. And in chapter 7, we close by analyzing in this distribution, contact pressures, the center of pressure, and the reaction causes, and we try to relate this to the underlying mechanisms behind PFO. So we're going to start with chapter 3, which is the guidelines that we developed. So we call this systematic development of lower limb in silico models for substitutional procedures. Our motivation of this is that we know all that in silico models may help, and a lot of people promises a lot of them, but we know that in order to really make an impact on the clinical field, they need to be developed in a safe environment, they need to be reliable, and they need to be affordable. And for this, we propose a systematic approach to develop finite element method simulations guidelines for surgeons. And these guidelines are easy to replicate, reproduce, and repeat. Very straightforward. So, the simulation process, there is a lot of ways to do FEA or finite element based simulations. But what we intended with this chapter is actually to just put it very straightforward, a guideline for making new people, new young engineers, young scientists, young clinical personnel in order to actually take out something without easy. We start by defining the objectives, data availability and acquisition of the data. With this come, of course, a lot of topics like ethical committee, how much is my region of interest, where I'm going to get my data, how I'm going to process my data, and all this is as well explained in the document that you have if you have more interest on the details. But we actually just propose a straightforward approach that if you follow it, there's a lot of branches extending out from it, but actually you will probably get something out of it. And the value added of this chapter is actually to create, at least for yourself, a standardized method that you alone as well can reproduce and others as well can reproduce them. Because we want to ensure consistency studies. For this work in these 3 years, we made hundreds of simulations, hundreds of them. And imagine that for each of them we had a different method to follow. I think it was not going to be actually relevant for ourselves. So we want to improve this decision making because surgeons or medical staff can explore different scenarios. But if they follow guidelines, at least they can get the same results at the end. We want as well reduce experimental costs, and I not only talk about financial costs, I talk about as well personnel, expertise, training, resources. And because we want to streamline the modeling process. Personalized medicine is as well very important. Every patient as well, depending on your way you get the data can be different. And if we, as I just mentioned, if we do something different for each patient, we're going to get different results. And regulatory compliance is very important. And at least if we follow always the same process, the same approach, we have something to use as a reference as well in order to comply with regulatory standards. And this is very, very important education and training. If you follow these guidelines, you can assess young surgeons, young engineers, give the possibility to actually do something auditive in a very straightforward way. With this, we jump into the first technical chapter, which is called the proximal fibular osteotomy versus high fibular osteotomy and in silico finite element study. Out of this chapter came a small proceedings paper, peer review by the FMBP in Springer. And of course, we have our ethical committee, we got all the data in order, and we started by developing a method for this. We had some patients diagnosed with clinical. I'm talking about real patients. And it was part of the diagnosis plan and for the treatment plan, pure tomography, pre-surgery had to be done. So out of this, or after this, of course, the treatment of the patient was the first part of this. Or research was not taking part into the treatment of the patient, that's clear. But after this, with the same data of the pre-surgery, we actually took the data and construct two models. One pre-operative finite element model and one PFO finite element. And with this, we compared and we evaluated the distribution and contrast what we wanted. And after 3 months of healing, application of HTO, took again a computer tomography, and we developed a tilt model, which is a post-HTO final element model. And of course, we want to compare the results. What we found out is that when we took the mechanical system of the whole limb, we saw actually a load shifting happening from the to the tibial bone. Because now if there is no tilt part of the system, then somewhere they need to flow the forces. The forces, they cannot just disappear. What we noticed as well is that the maximum stress on the tibial bone increases by around 5% in the tibial bone, but it's more homogeneously distributed through the whole leg. And the stresses along the femur is as well more homogeneously distributed and slightly decreased after PFO. This is what we saw for the whole stress. And we noticed as well an improvement of the axial alignment, but not as much as when compared to the HTO, or after the HTO that you have here. We analyzed as well contact pressure. In the knee joint, this is on the tibial plateau, on the cartilage, on the other half. Before the surgery, the contact pressure was higher in the compartment, you can see here. And after the in silico HTO, overall contact pressure was reduced and well distributed. And after the in silico PFO, pressures were reduced and they were slightly shifted to the lateral compartment. So it kind of matches the theory of what is happening. And the oscillating pressures are redistributed along the both compartments. Talking about stress distribution, similar behavior. Before the surgery, stress at the medial tibial plateau was higher than the lateral compartment. This is to be expected when a patient is diagnosed with the medial compartment. And after the in silico HTO, overall stress were reduced, very distributed. And after the in silico PFO, stress were reduced and slightly shifted to the lateral compartment. Again, similar trend in the stress distribution. So the conclusion of this chapter is that we saw and we found a trend for loads and pressure shifting to neutralize both compartments. And however, after PFO, the stress concentration increases in the lateral compartment, increases on the tibial bone and femoral bone due to the lack of fibular stiffness. So if we take, as just mentioned, one part of the system down, then forces need to flow. And with this, PFO may actually act something similar to what HTO is doing, and maybe can be an alternative for it. The take-home message for this chapter that I wanted to take you is that there is stress distribution, or stress distribution and contact pressure will reduce and slightly shifted to the lateral compartment after PFO. With this, we jump into a little branch that we took out from this research, and we wanted to analyze the biomechanical properties of the meniscotibial popliteus fibula complex. Big name. So what we wanted to do with this is actually take a look into many other relevant substructures of the knee joint that are usually omitted when we do biomechanical studies of the knee joint, and they are usually ignored. And like those of the meniscotibial fibula complex, and they are usually stabilizers. So what's found is that the damage of these components has actually been associated as well with meniscal structure, and the reconstruction of these elements has been proposed an effective method to reduce the phenomenon of meniscal destruction. And the idea is that the parameterization and implementation of accurate material models, or a small material library, is not there. It's not yet there for such elements. So we developed an hypothesis that the biomechanical properties of the complex can be quantitatively determined using dynamical mechanical analysis and uniaxial tensile tests. We followed the method. We took some samples out of cadavers, and then we prepared them. There's a whole bunch of process and preparation as well stated in the document if you want more details about them. And then we planned just two processes, dynamic and mechanical analysis and uniaxial tensile tests I just mentioned. And we just wanted to create a small material model for them in order to later on use them in finite element simulations as well. So the results, pretty straightforward. We found and developed an elastic models of the complex human being, as you can see from the lateral ligament. And we thought, well, the ultimate tensile strength, this is pretty common variables in order to use in finite element simulations, and the ultimate tensile stress as well. We developed actually different models. We use a geo model in order to develop, to as well try to represent the material characteristics, and as well a new model, and we found out that the new model that we present, it was a little bit more accurate with the results that we found out. And from the dynamical mechanical analysis test, we found as well a complex elastic modulus for the materials or for the ligaments, and we found as well the glass transition of the elements, that it was happening around 70 degrees Celsius. And this was actually pretty straightforward for the results in order to develop the model. And in conclusions, the proposed material characterization approach is effective in providing essential data, fundamental data for the mechanical description of these ligaments. And with this, we generate a small material library in order to implement them in FEA commercial software. What I want you to take home about this chapter is that we expand the material knowledge of substructures of the knee joint, and this may increase the future in silico models. With this, we go again to the main branch of the project, which is the in silico study of the biomechanical effects of PFO on knee joint, contact pressure in varus valgus. Out of this project came out a publication in a medical engineering physics journal, and the motivation of this is that we know that each patient presents unique physical conditions. Every patient has a different condition, maybe because they went their life working, doing sport, doing some activities, they did something, they did the other, they had injuries. Doesn't matter what, but these conditions may actually have influence on the effectiveness of PFO, and like the varus and valgus malalignment level on the knee. So we hypothesize that difference in hip, knee, ankle angles lead to different pressure distributions, and therefore different center of pressure locations. And therefore, proximal fibular osteotomy will report as well different outcomes depending on such initial conditions. So we went and developed a study, and then we wanted to explore the effects of PFO by varying the hip, knee, ankle. So we wanted to analyze the contact pressure distribution of the lateral cartilage and the medial cartilage of lateral nerve compartment, and we wanted to check the variation of the center of pressure position. We wanted to check how the center of the knee pressure was located before and after PFO. And we use common malalignments that are found out in clinical studies. So, we started by taking a reference model. This reference model has a neutral standard position, I would say, in which has an HKA angle of 180 degrees, or it is actually not. It has no malalignment. And we found out that the average contact pressure is actually similar, a little bit more in the medial compartment and a little bit less in the lateral compartment. Matches actually the direction. And after PFO, we found out that the lateral compartment was loaded a little bit heavier, and the medial compartment was unloaded. But if we take a look to the center of pressure, the original, the before PFO center of pressure, is going to be from now on marked with a point. Yeah. We see that the center of pressure in the knee, it was in a normal alignment, was in the middle. After the PFO, we are further away of the center of the knee. So, which means is that if you have a healthy knee and you apply PFO, you may get worse. Yeah. Makes sense actually. And after that, we start to analyze the tibial deformations in varus. So if you see here before PFO, the center of pressure is located in the medial compartment, and this is getting further away from the center of the knee as we increase the varus malalignment. After the PFO, marked with a cross, the center of pressure tends to reposition itself into the center of the knee, which means is that actually the PFO is reallocating and is neutralizing the center of the pressures in the knee. And as you see here as well, of course, the medial compartment, it's get alleviated from pressure. which is actually doing this work. But actually something very interesting is that for small deviations of values, PFO looks to work actually quite good. But as we increase the values of malalignment, the effectiveness of PFO tend to decrease, which is actually pretty interesting. If we take tibial deformations in valgus malalignments, something similar, in valgus, the center of pressure is of course located in the lateral compartment, and as we apply PFO, it tends to shift, or it wants to go into the center. It tends to relocate to the center, but actually the effectiveness is not that much, which is actually something kind of expected. If we are in a valgus position and we take out the lateral support, should not be that much effective, but it seems that the pressures are redistributing as well. Because even if you don't have the mechanical support, the forces need to flow. So what we have here is an overview of what is happening in the tibial deformations. So these field forms are before PFO in valgus. Before PFO in valgus. After PFO in valgus, they tend to go to the center of the knee mark. Tibial valgus, these symbols here which mark the lines at the end, and in the outside, so before PFO, and after PFO, it's not that. So it tries to, but the effectiveness is actually low. So we did the same as well with femoral deformations, and you will say, but is not PFO intended for varus tibial deformations? Yes, it's intended for, but if there is no biomechanical evidence for femoral deformations, and we have the possibility and the advantage of doing these studies in silico, then let's do it as well in silico for the femoral. So, for the varus deformations, we found out a similar tendency as well for the tibial varus. I'm not going to dig that deep, because if you take the system as a system of triangles, it's actually kind of the vice versa of what we already saw in the tibia. So, it tends to work, not that much increase in the valgus. Valgus is very interesting, as we saw in the tibial valgus deformations. PFO was doing something, but not that good as in the valgus. Here is actually getting worse. If you have femoral valgus and you apply PFO, then after PFO, the center of pressures is getting further away from the center, or at least even from the original position, which is actually pretty interesting. As well, an overview of the general before PFO in femoral valgus, after femoral valgus, before femoral valgus, before femoral valgus, is getting further. The conclusion is that in varus deformity, PFO helps to evenly distribute pressures between the medial and lateral knee. However, in tibial valgus, and femoral valgus deformities, the effectiveness of PFO is less significant and even detrimental in femoral valgus deformations. And this actually correlates pretty good with some studies reported in the literature, actually in 2019 and 2023, that PFO is more effective for mild valgus deformities, less or equal to 5 degrees of valgus deformations, and is less effective for deformities of equal or greater than 5 degrees, which is actually consistent with what we saw in this study. As greater the varus or the valgus deformation, the less effective PFO is actually become. So the message that I want you to take home from this chapter is that valgus and valgus deformities matters in the biomechanical impact of PFO in knee joint concentration or pressure redistribution. And that's how we come to the final chapter from this, or from the final technical chapter of this presentation. As well, out from this chapter came a paper that was published in Journal of Orthopedic Surgery and Research, and we wanted to analyze how effective is proximal fibular osteotomy in redistributing joint pressures, which is kind of the same as in the chapter 4. But we wanted as well to use the insights gained from the previous chapters and combine everything together. So the motivation is that we wanted to establish correlations between biomechanical variables, or we already analyzed stress, we already analyzed contact pressure, center of pressure, but this is still something missing. No? We are still missing something, how it relates actually to patient-specific data on the effects of PFO, and how we can take back the question from the beginning, how we can explain actually why it works. And we developed an hypothesis that PFO, as we already studied a lot of years, has a significant impact on the distribution of contact pressure within knee joint of patients with medial compartment osteoarthritis and edema, resulting in similar outcomes as HTO. The methods, similar methods as well as we already planned in chapter 4. If you want to take a better look to them as well in the document, this is everything there. We had for this chapter, we have 5 patients, 4 men, 1 woman, 40 plus 10 years age, and weight around 8 plus minus 10 kilograms. They reported pain on the medial side of the knee joint, and of course, one of the knees on each patient was associated with severe intervallos. The following important from this diagram is actually that we used as well the same approach as before, and we developed as well 3 models: the PFO model, the preferative model, and the post-HTO. And we designed this study similar as we already gained of insights and experience, and using the experience gained from this and from the previous chapters, we combined everything together with as well patient-specific data. And we found out something very interesting, and I think it's one of the core points as well of the presentation. We found out that before osteoarthritic knee, the reaction forces happening into the proximal tibia. In the medial side of the tibia, they were acting in compression. And the lateral side of the tibia in traction. And interesting as well, of course, the fibula is doing something. Fibula, I don't know if you can see it here, but the fibula is as well pushing into compression, which is actually amazing. If we take a look as well to the previous images. After HTO, medial side, completely in compression. Here as well, in the lateral side, it's like a mix of compression and traction, but mostly in compression. Here, I hope you can see a little bit. And the fibula is acting as well in compression. The interesting, of course, is that after PFO, it's changing a little bit. Of course, the fibula is exerting no forces, so it's out from the system. And the medial side of the tibia is acting in compression, but as well the lateral side of the tibia is acting in compression. We're going to take a look a little bit deeper into this later. But it's actually very interesting that we found. It changed actually the reaction forces from before. We analyzed with the insights as well as I gained from the previous chapters. We analyzed the before surgery. The higher contact pressures can be observed in the medial compartment, always in the medial compartment, higher pressure. And post HTO, contact pressure more homogeneously distributed. And medial compartment was reduced across all patients post HTO and as well after in silico, as you can see. And the lateral compartment contact pressure was increased post HTO and after in silico before. So the tendency is kind of similar. We analyzed the center of pressure for all of the patients that we had, and we took the same procedure, same images in the center, pre-op SUP. I hope you can see as well. Something is very difficult, otherwise this is well in the document if you want to take a look a little bit better. And after both HTO and PFO surgeries, the center of pressure deviations from the center of the knee was reduced. It's actually, it tends to go to the center. In all patients, the preoperative center of pressure was concentrated in the air compartment. They were diagnosed with intervallos. Again, this was to be expected. And following HTO, the COP tends to return or approximate to its position to the center of the knee. After in silico PFO, a comparable effect can be observed. And the COP is moving closer to the center. In conclusion for this chapter, we analyzed the tendency of the center of pressure variation, or the tendency of the center of pressure variation is similar between in silico PFO and HTO. And this is very important as well. The efficacy of PFO in this case was assessed by analyzing the contact pressure distribution or the joint pressure distribution and not the malalignment. we're going to take a look as well to this later in the outlook. And by analyzing the reaction forces, before the surgery, major compression forces were transmitted by the medial side of the tibia. And with 3 cortices, we're taking back as well the theories of the PFO. The lateral side of the tibia was under traction, as you can see. And with 2 cortices, or PFO, the lateral side of the tibia is acting under compression. So something very important from this chapter. And what I want you to take home is that tendencies of joint loading after PFO are similar to those observed after HT. So general discussions. Well done with the technical part of this presentation. More. So we wanted to respond to the general hypothesis during our research questions. So otherwise, it make no sense what we do. So we need to discuss the principal findings. So if you remember the first question was, what are the differences in mechanical behavior, stress distribution, knee joint contact pressure between HTO and PFO? Entonces, it's clinical implementation. Behavior. Center of pressure towards the center of the knee after HTO. Yes, we see this behavior. We can actually see this. After PFO as well, maybe less, but the tendency is as well. The behavior is there. Contact pressures in medial compartment are reduced after HTO. Yes, we see that, and after PFO, we see something similar. Homogeneous distribution of contact pressure at the tibial bottom. After HTO, we see that. After PFO, we see something similar as well. The stress shift and homogeneous distribution of the whole. We're speaking of stress distribution now. After HTO, we saw it. And after HTO, something important as well is, of course, the implants are taking some of the stresses. And after PFO, the femur, it's happening. We see the behavior, but not in the tibia. In the tibia, it's actually being more concentrated into a part of the tibia, so there is no complete homogeneous distribution in the tibia after the PFO. This is actually to expect, as I just mentioned before, the forces need to flow somewhere. And we take back, answering as well this question, I want to go back to the theories. And the first one is the theory of the non-uniform setting. As we saw this here, after this is looking more homogeneous after PFO, is that maybe the support of the fibula, or the support of the fibula given to the lateral compartment is, this does not allow the lateral compartment to settle down. And when this support of the fibula is removed, we actually are allowed the system from the lateral side to settle down. As we see by analyzing pressure, something similar, it's settling down. And after both PFO and HTO, our compression form is observed in the lateral part of the tibia. So, which means that the mechanical system is allowing itself to go back, to settle down into its position. By analyzing the theory, or by taking a look back to the theory of the too many cortices, the results indicate that having 3 cortices during the advanced misalignment causes the lateral tibia of the, to go into under traction. The lateral part of the tibia to be under traction, which is this. And then, after PFO, these tibias are used to compression. So what we see here is that in an osteoarthritic group, the forces they are not balancing themselves in compression and traction. And the fibula is as well in traction. The medial part of the tibia is heavily loaded in compression, and the lateral part of the tibia is acting into traction. So maybe it's more compression into the lateral side, more traction into the lateral side. And after PFO, because the fibula is not acting anymore, now the loads are balancing in a more homogeneous way. So this is something actually very interesting in order to maybe answer or support as well the theory of the too many cortices. There is too many cortices in the system, and this is generating with age as we grow old an imbalance in the load distribution. The second question was, what is the influence of various values, anatomical misalignments of a patient lower extremity defects review. And can such initial conditions be related to trends in change of stress distribution and the center of pressure? And we actually could answer a little bit of this by our in silico studies. This is the tibial varus, we already saw it before, and there is actually an influence. And yes, such initial conditions, they can actually be related to trends in change in the stress distribution and in the center of pressure. The big question was a more general question, which was if PFO is feasible procedure to restore hemodynamics, and how can we conextion this procedure without compromising patient safety. The tendencies of joint loading after PFO are similar to HTO, so if it is feasible, we try to answer by comparing with a really standard procedure that is already there. So the tendencies are similar. And what we saw as well in our studies is that PFO may only be suitable for patients with mild varus deformities, less or equal to 5 degrees of deformation, and less effective for severe varus deformities. So what we want to actually to complete the answer of this question is we don't want to tell the medical community that PFO is a better solution for as HTO or is a replacement for HTO. We are actually trying to establish surgical indications in order for the medical community to decide and take decisions on to where maybe makes sense to apply a procedure like that, based in the biomechanical evidence that we derive from these studies. This is also very important. So with this, we finish the technical part, and we are going to start to making our way through the end line of the presentation. We want to take a look to the outlook, to what actually was still open, was maybe not in scope of in these 3 years, and what we actually want to do in the future. We want to actually expand data, we want to expand the data availability. We spoke about maybe 5 patients at the beginning, 10 patients 10 patients in the beginning, 5 patients after. But as you already know, data availability is very complex always, and as well for the studies that we conduct. So we want to enhance them by using more data. And of course, as you saw, we use full-length CT scans in all of our studies. And this is not always very easy, and it comes with disadvantages. So we want to analyze how can we get the same results that we got into these studies by not using full-length CTs, maybe by using a sensitivity analysis of the region of interest, maybe reducing it, and in order to not use the full length of CTs, it's not always easy. And of course, we have as well stricter numbers and set of boundary conditions. And of course, this is limiting the bone range. So we want to make our way to different motions to improve the boundary conditions in order to increase as well the accuracy of the models. Something very important, of course, in the document is that these are static simulations, and we want to expand as well into transient dynamics simulations in order to not just analyze the behavior of the system in one point of the time. For example, maybe gait analysis, maybe by sitting, by extending, or I don't know, but that's what we want to do as well. We want to incorporate as well different muscular forces, and as we saw in the chapter 5, secondary anatomical structures, not only the ligaments, not only the cartilage, but we want to increase as well the fidelity of the model by including more and more boundary conditions, or in this case muscular forces, or more structures. And of course, the elephant in the room, we want to validate the models that we propose in this work by actually laboratory and clinical investigations. This is one of the, I would say, the critical points to do after this, in order to bring a little bit more of validity to what we already did. And with this, we jump into conclusions. I'm just going to take back a few of the images that you already saw, just to give you a better understanding of it. We saw a trend for low and pressure shifting to neutralize the medial lateral compartments, and this was reported medically. After PFO, stress concentrations increase on the tibial and femoral bone, as you can see here, right? It's a little bit more stress here, and a little bit of stress more here. And because of course we are a part of the system is not there. And taking as well the chapter of the material characterization, we propose very fundamental material data in order to include such substructure that we want to include in the future, and we propose a very basic material library to add them into the finite element analysis. In value deformity, PFO helps. And to heavily distribute residual linear and Laplace compartments. In trivial values and thermal values deformities, the effectiveness of PFO is less significant or even detrimental for femoral values. PFO is more effective for minus value deformity and not that much for severe values. Tendencies of joint loading after PFO are similar to those observed after HG. However, in trivial values and femoral value deformities, the effectiveness of PFO is less effective. And again, with this picture, having three cortices doing various malalignment subjects the lateral part of the tibia to traction, and following PFO, this side of the tibia is subjected to compression. So this was the end. And I just want to give you a very brief timeline of what was the project. This project was, or this research was intended for 3 years. And this is what actually kind of happened after the first 12 months. We got here the dress proposal, and then submission of one paper, submission of the other paper, submission, and at the end we got three publications after this. This is the official timeline. But the unofficial journey is actually started in 2018 in Germany as a research scientist. And I came all my way this as well in parallel simulation engineer. So it was not an easy journey, that's what I want to tell you. It was full with a lot of things, and we came at it, I think, in a pretty well. Thank you very much to my supervisors, Jill and Antonio. They are there. Incredible performance, and I'm very thankful for it. Thank you for the members of the tribunal that is here. I took the photos that I found. I hope they are okay. So thank you very much for being here. Thank you very much. And acknowledgement, Dr. Simone Perelli, you saw it before. He was the one, actually we came with this idea like 4 years ago or something, and we started to develop the whole research output. Dr. Morales could provide a lot of data that we use into this research, and of course Dr. Carlos Mojao for supporting this whole clinical data acquisition. My family, of course, if I don't put my family here, they're going to kill me after. So they are of course part of this, my Mexican family, my German family, so thank you very much. And of course, special thanks to my partner that's as well there, and that's what we do today. Thank you very much, and I hope you had a nice time.
I'm lacking. So I'd like you to discuss those points, please.
Yeah, so PFO was introduced not that long time ago, so this already tends to not have that much clinical studies about it, even if there is a few. So there is no that many long-term analysis of what actually is happening in the long run with the patients. Most of the studies that are out there, the clinical studies that are out there in the literature, they are talking about short terms and maximum 2 years of analyze what is happening with the patients. So short terms is relieving pain, like literally immediately after PFO, the patients say they report immediately relief of pain, the joint narrow, so the joint cavity is expanding, the narrowing is decreasing, and the functionality of patient is literally a few weeks after they say it's better. So the function of the joint is much, much better. All these studies as well, I think they are more focused as well in the short term, because first of all, the lack of comparison studies that we can do of all results with long-term studies. And yeah, the objective of PFO is that they can immediately relieve pain, increase function, and if in the long term the patient goes back again with pain, you can always perform an HTO, or you can always perform continuous pattern test. So that's the main idea of this. So maybe you don't have the resources, maybe you are in a developing country, or maybe there's no personal expertise, so you can always you are actually maybe okay for a PFO. We can do that, and if after 5 years or in the long term you are not getting better or you decay again, there is always a chance to perform one of the other operations. So that is for the long term, but unfortunately there are no many clinical studies reporting on this. That is something that I think we are going to see in the upcoming years. But as I mentioned, in the short term, pain relief, improved function, joint closure or joint narrowing is decreasing and is increasing. So that's more of the idea of PFO in the short terms. And the simulations, I think they tend to answer into that one. Yeah.
And then about the sex differences?
As well as we report, there is one study with 47 patients. They report, and they report in general. So I don't remember seeing studies reporting as well on the sex differences. I mean, statistically, of course, but I don't have in mind exactly what are the effects of the PFO varying on women and men. But I think depending on the variables that we can analyze, maybe weight and the generation of cartilage or maybe malalignment, I think at the end, if it is a woman or if it's a man, if the varus mass alignment is a variable that we can control, maybe we can predict as well the results. But I will need to take a look into that matter depending. But as I just mentioned before, unfortunately, there is not that many studies that I can really say, yeah, I have an answer directly for the age difference or age size difference or weight difference or country difference, of course. And there is not that many. This surgical intervention is mainly performed in China and it's mainly performed in India. As I just mentioned, the lack of evidence, I think is still holding this surgery to be more practiced here in Europe. So the data is actually not that much available for that.
Thanks. I'd like to further discuss this a little bit. So when you make surgery on a patient and then you cut a piece of bone, so you have bleeding, you have a risk of infection, and as there are some medical doctors here in the room who might contradict me. But this is my understanding of many years of collaborations with orthopedic surgeons. So then they tend to weigh very carefully the risk benefits. The thing is that in general, as far as I know, and at least for total knee arthroplasty, if you're in a reasonable health system, so you tend to use that as a last resource because it's invasive, and HTO or PFO are invasive too, less than knee arthroplasty, but it's still invasive, and you cut the bone, and then you have those risks. So what is the typical profile among the patients that benefit of that? Because if you consider that it's last resource, no? would you take the risk then to do, a first surgical operation, then on the bone, knowing that maybe in a couple of years you would go anyway for total knee arthroplasty, or there is nothing to do, and then when you're doing that, so when you do a total knee arthroplasty, you're solving the problem of inflammation in the knee joint that contributes to pain, and because there is no knee joint now. When you're doing this operation, you're not solving this. You still have synovitis, you still have inflammatory factors, cartilage, progressive innervation, etc. So these are a lot of questions here. And so according to your knowledge, now, what is the typical profile of the patient if we put aside middle incomes, low incomes, in a more generic way?
There is a lot of studies as well that are reporting the use of this procedure. I'm going to add my knowledge. And they tend to use this PFO as an option for young patients that they want to avoid actually the replacement of the knee or the use of implants. But they are young, they still have mobility, they still want to do many other functions. And in order to avoid those implants, in order to avoid the replacement of the knee joint, they actually tend to use this, to do this as a resource. Not as a last resource, but as a first resource. So we apply this, your body is going to get better, you still have the functional technique, you still have your knee, you still have, but if you recay in a few years, it's still the option. So this surgical operation, at least in what you can see from studies, it is intended for actually people that is still with a mild varus, not that advanced in osteoarthritis. That's why probably the age is well an important factor, because as we go older, probably the malalignment is well going to get bigger. So they tend actually for young patients in which the replacement of the knee is still not something to play with. Or maybe you can avoid it or you can postpone it. So that is fine. And I will take actually not of a less resource, but actually maybe something simple, because PFO is stated as simple and straightforward. Everyone you read PFO is simple and straightforward, but of course it has a lot of complications. So that's why, because if they say simple and straightforward, they use it as a first resource, and then if it still gets complicated with the years, there's another still a chance. Yeah, I think as well, for example, young people that the varus deformity is not that big, as well depending on the country that are you. As I would say, for example, in developing countries, maybe you cannot pay implants, maybe the surgeons are not there, the personnel is not there, maybe cutting the bone is easier and faster than something different. Because of course there are complications. You mentioned complications, for example, it's not cutting the bone is easy, but getting to the bone and cut it exactly where you need to cut it is a different. There are nerves in between. You can cut more than you need. Bone healing applies as well. So this is what complications. But I will use it as a first resort. Yeah.
So basically you're paving the way to my next question. So then if we assume that the profile of patients would rather be a still active person, which would like to put implants that has an effective life of maybe 15 years, or even 12. So when you do, in contrast to HTO, so I understand that PFO gives freedom to the musculoskeletal system to readapt itself.
Yeah.
Because you're just basically relieving an internal load by cutting biological structures, the fibula, and then so everything can reorganize. So of course, it will evolve a long time.
Yeah.
So what you have a few weeks after the surgery might not be what you have after rehabilitation, after the patient is back to full active life, etc. So in the light of these considerations, how do you think your very conclusions about the field of applicability of PFO and then the promising aspects of PFO are valid?
I think they are valid to some extent. Of course, as you mentioned, actually perfect. We are allowing the system to reaccommodate itself, but we are not avoiding the regeneration, bone healing loss. I mean, bone regeneration is going to happen. At some point, bone is going to be there. At some point, the system, of course, is going to as well readapt itself to its original position, probably. So maybe in the long term, maybe it's something that postpones the inevitable, if I will say, maybe in 20 years. But as you mentioned as well, TKA or HTO as well probably has as well an end of life at some point. So I think maybe a good solution for maybe as well 10 years, 15 years, depending. I think as well as we grow older, maybe the bones are not going to heal as fast as we are younger. I think it's a promising solution for specific applications. I think as HTO, as TKA, we cannot control that many things. We cannot control what people do after an HTO. We cannot control if people lose weight or gain weight after an HTO. And inflammation is going to be as well there. And I think it's very promising for a few scenarios. But probably in the long term as well as other surgeries, we are going to have drawbacks. That is something that we cannot take away. Yeah.
But then maybe one of the promising aspects of computer models and simulations here would be then to approximate this probably the time evolution and recommend specific physical therapies that have to go along with this very specific surgical procedure to maximize the rate of success.
So in this work, we're playing literally at the edge of what people is doing in terms of PFO almost. So you mentioned a pretty keyword, computational models, they are not only finite elements. They are people that is modeling bone healing. There is people that is modeling more dynamic simulations of the patients. So after this is the fundamental baseline of what people can after do with this, with the effects of PFO. Of course, there's a lot of people that is going to start to analyze what is happening with the joint dynamics after walking 100 meters, and there is going to be people that is going to start to study what's happening with bone healing using computer simulations after 2 years. And of course, more people is going to come into the game of what's actually happening behind people. As you mentioned, this is still very, even if it is 15 years old, I would say, the surgery, there is not that many studies that can really help in order to know exactly what's going to happen in the future. And computer simulation, I think, is just starting. And that's why this work.
So it brings me to the few whys I have.
Yeah.
So my first why is you've done your PhD thesis in a research group that is extremely strong in motion analysis, multi-body dynamics, and you would have had a great opportunity to better define your boundary conditions and maybe better address the question that we've just discussed here. So why haven't you done this?
I think that's a very important thing, of course, for any research to clearly define from the beginning what is in scope and what is not in scope. Of course, the research group of my supervisor is very strong, multidisciplinary, motion dynamics, dynamic analysis. But we wanted to first to analyze what is happening. I mean, if we cannot even explain what is happening in a single point of time in the mechanical system, I think we would have taken a lot of risks, tried to make this complex, the system complex and complex, if there is not that much information that actually explains the basics of what is actually happening with the system. So we decided from the beginning to take one step down and say, okay, let's start to analyze the mechanical system as it is, standing position, load distribution, and let's see what happens. There was no reference actually to based on gait analysis or sitting or any other primitive motions. So I think the understanding of the basics and the mechanisms is what we actually intended to do this work. There's a lot of research opportunities, as you said, but I think there will be not really in the scope of what we intended. We wanted to really, first of all, focus on the basics and fundamentals of the mechanical principles of what's actually happening after the kind of PFO, before going to this is happening when it's working, this is happening when it's there, because we have no actual reference of why units is working. So the opportunity is there, and I think that's why a lot of other people can come around and continue the research, or even myself with the validation of these static models, cadaveric in vitro studies, maybe some practicing, because our research group includes as well surgeons. So step by step, and for sure one day we're going to be there. Yeah.
Okay. I understand your answer. I can't disagree with how you have defended it. I think if you don't have the right boundary conditions, someone can come and say, oh, what you've done is worthless.
Yeah.
I would just tend to say, so this is a whole picture we want to achieve, and we have to start from a point. We have decided to start from that point.
Exactly.
I wouldn't say it's more important.
Yeah.
That's not.
We wanted to start from something and have a baseline. Of course, there was a lot of discussions through the years, muscular forces and this and there and that, and yeah, but we don't know actually what is happening from the beginning. So, yeah.
Thanks. And then another way I have it's more technical. It's so you've done experimental testing, and so you might have had the opportunity to validate your lawn models, and you've not done it, so you don't have a validated model, which is a huge weakness. I understand that it's not an easy job. I would have expected a bit more discussion about this, about the lack of validation. I'll come back to that in my last question. If you really and but okay, so you've characterized then basically a soft tissue, and you've done, in my opinion, a complex dynamic mechanical analysis in order then to assess the dynamic modulus and the role of the dynamic modulus. I don't really understand why you've taken that strategy. It would have been so easy to do a stress relaxation test under axial tension, and in order to find your relaxation types of Maxwell, of a generalized Maxwell model. So why have you taken this strategy?
Yeah, we started with this research a few years back ago as well with other soft tissues, not exactly anatomical soft tissues. And we decided that in order to try to get the most out of the viscous behavior of the soft tissues, we wanted to analyze as well the dynamical mechanical temperature analysis, how it was reacting because of temperature. So we actually kind of validated the uniaxial, because we did the uniaxial tension test, straightforward, and we took then the basic elastic modulus, ultimate tensile strength, Poisson ratio, most basic elastic properties. And with the dynamical mechanical analysis, we tried to first of all validate as well the elastic modulus by using complex elastic modulus, and as well initial shear stress, chronic series parameters are well to put them into the simulation software. So we wanted as well to take a look to what's happening to the tissues with the temperature. Knee joints as well is a tissue that is under a certain temperature, and we want to analyze as well that we are not missing something that is happening at 35 degrees. We are not something that is happening at 40 degrees. Maybe the knee joint is not going to be not going to be never at 50 degrees Celsius, but as you know, soft tissues, they may change their behavior depending on the temperature that they are taking. So that's why we want as well to view dynamic mechanical analysis complex with temperature factors, just to see that we are not missing something. And actually what we saw is that until 70 degrees approximately, we were not missing something. So we just kind of cross-validated what we did, and not something like temperature or different strain rates is playing something, or frequency is playing something with the model that we are getting. So we actually cross-validated what we did with the axial tensile test, and we took a little bit more of parameters of the viscous more elastic running parameters. We took them as well into the simulation.
And that will be my last question because time is running. So I haven't seen in your report, or I haven't heard in the exposition, the standard VV240 from the American Society of Mechanical Engineering. Are you aware of this standard?
No.
You should.
Yeah.
You absolutely should be aware of this standard, especially if you're continuing this work or if you're continuing in the field. It's a standard that settles all the good simulation practices and steps in order to position in medicine and then in the market eventually with certifications, modeling and simulation technologies.
I will take a look at that.
So that's VMVUQ stands for verification, validation, and certainty quantification. The American Society of Mechanical Engineers have been working on this standard since many years ago, I think, nearly 10 years, probably. They had several iterations. The FDA has now accepted the standard in order to consider digital evidences on software as medical device or decision support systems. And yeah, I think it was, I think in such kind of thesis, it should become mandatory to include that as quality, as quality check. So we won't discuss it because you haven't looked at it, but I strongly recommend you to examine it in your next step of your professional career.
I will definitely.
Direction, of course.
Definitely, I will. Yeah, thank you.
Thank you.
Just saying that actually the European Union's medicines approval agency also requires.
Yeah, they have it approved.
So the FDA were on here first. What I'll do is I'll let Lydia ask his questions next.
Okay.
So we'll just get the chemical concept.
Okay. First of all, let me give you my congratulations as quality engineer, because from a point of view of a surgeon, not the only surgeon of this room, or but it's an interesting job, because normally me surgeons, we usually don't take into account a lot the fibula when you try to correct this kind of deformities or all the Barrett's deformity. I mean, it's absolutely irrelevant that there are many population, young people with medial peyronie and with Barrett's deformity. This is a really headache that we have in our real visits. It doesn't mean that it's a real study, and let me say, curious study, because normally we don't think about the fibula. My question is about probably a different focus than engineers, and I'm aware that you are an engineer, not a surgeon, but probably in my mind when you are reading your text, probably I have some anatomical considerations, because, for example, when we normally perform a valgus osteotomy of the tibia, usually sometimes we have to make something maneuvers to the fibula. Sometimes we just dislocate the proximal tibiofibular joint in order to avoid or to permit the sliding between the fibula and tibia. Sometimes we make the osteotomy just on the head of the fibula, just on the top of the fibula. And I think you decided to do all these models, taking or removing just 2 centimeters at 6 to 7 centimeters from the tip of the tibia. From an anatomical point of view, we know that there is a solid connection, so a membrane that connects the fibula and the tibia. And furthermore, there are some different shapes and some different orientations of the proximal tibio-femoral joint. Sometimes the fibula is just really horizontal, probably, I don't know exactly because I am not engineer, but probably the forces are applied different to the tibia, and sometimes this joint is more vertical. And we can see, because they are actually, the surgeons, we use some classifications to relate this. My question is, do you think if you take into account different orientation of this osteotomy, or to make the osteotomy in a different level, could we achieve really different results than in your case? Or maybe it's not important, this?
We were actually talking about this before the presentation. There is one study as well that actually cuts open in different locations the fibula, and they came out with like the same results. Maybe if you cut the fibula head in a different orientation, maybe anatomically, for sure have different effects on what is actually happening in the joint. But for the mechanical point of view, if you cut it 1 centimeter after the head, 10 centimeters after the head, or 15 centimeters after the head, or below the head, it's actually the mechanical system disconnects itself. So as you saw in the video, in the image of the force, maybe I can see it here. I mean, if you cut it here, you cut it here, the reaction forces, they are going to be 2 tend to 0.
Yeah.
Yeah, I mean, we actually did this at the beginning. Of course, we test a lot of different simulations. But I think the important thing from your question is what happened with the orientation of the fibula head. The orientation of the fibula head, maybe cutting different, really proximal there, maybe can have different effects. But I think as long as the system disconnects, of course, as we just mentioned, there is no membranes of the body condition, there is missing as well muscular fat. There is a lot of things that are fluid as well that probably has a different effect. But I think overall the tendencies are not going to change. The tendencies and the trends of contact pressure redistribution of forces going to the tibia is going to be there. And I think at the end, I don't know if that helps when you do the surgeries, but maybe, I mean, I think it may have an influence as well. I don't think, as long as the mechanical system disconnects, I think the job of the fibula is actually done.
Then does it mean that if I say you, for example, that I prefer just to this, for us, for example, is a different surgery just to provoke a dislocation of the proximal tibio-femoral joint, than to make maybe an open surgery to remove. If it's the same, probably.
After the dislocation,
dislocate the proximal joint, avoiding to remove 2 centimeters of bone in terms of biomechanical distribution.
Anatomically, that's a very interesting as well point of view of even if PFO is actually required, maybe you can dislocate. But I think what happens at the end of after the dislocation, you dislocate the bone and you switch the position of the joint in the space. Is they still connected after dislocation, or are just moved?
But when you remove, there is a movement between the joints. There's a capsule, but you can slide, the femur can slide. Is that
that was also something interesting. We wanted at some point in the years ago when we were planning this varus valgus malalignment study, we wanted to as well to test the rotations, for example, what happened when you rotate the joint, and maybe some phenomenon like this we could have seen. If you rotate the joint, probably the fibula switch position, maybe you can have different effect. But I think at the end, what we saw as well here, for example, the patients, for the patients that we analyzed, the fibula was not always in the same position. Of course, the fibula is always changing. Maybe a little bit here, maybe a little bit behind. I think in this case it was literally in the posterior lateral behind, as you can see here, no? And the effect was actually the same.
Right. Yeah. Thank you. My second question was, my colleague has asked something similar, but from my point of view, I don't know if you agree or not, in this type of surgeries, there is a real relevant paper of soft tissues. It's absolutely mandatory to evaluate and all. In our clinical cases, sometimes we have to perform, sometimes we do force X-rays, to avoid the laxity of the patients, because sometimes when we try to correct the various disalignment and we have a laxity of the lateral compartment, we have a risk to overcorrect this disalignment. In these terms, probably the connection between engineers and surgeons, it's really important. The question is, you are committed in your limitations because it's just a static study, just taking into account a CT scan, X-rays. Right? Which kind of explorations do you need from us, from the surgeons, from the clinical, from the hospitals, in order to improve the prediction of your results? Maybe dynamic magnetic resonance. Maybe it's important to know the strength of this bone. In a really osteoporotic bone, we will have different results. Which data is more important, and can we give you in order to plan more efficient the surgery?
So one of the things that we made was, first of all, the deformity. The deformity is a variable that we can play with, the deformation angle. This is something very important, of course. But we as well want, or we have planned for the upcoming time, we want, in regarding to the model validation of our models. Maybe, for example, or we are planning with biomechanical machines in order to assess as well with the cadaveric bones as well. First of all, we want to check that we did is actually happening. Maybe the values are not the same. We do not expect that the values of stresses or pressure are the same, but we want to check, first of all, the tendencies that we are playing with. For example, we demonstrate that it is going from the medial to the lateral, but not that much for a values of 10 degrees. We put in the machine 10 degrees value deformation with cadaveric bones, and then it's happening something similar. Okay, this is something that we actually would like to cooperate more with surgeons, with the partnership that we have in the team, just first of all, to get through what we did with real bones, with machines, and to validate this. But what I want to say is, we want to first take a look to the tendencies, if it is happening. If the values are different, or if at the end the position of the fibula changes a lot, the results are going to be different. But first of all, we want to check that actually the PFO makes or has a tendency to do something. Because if we cannot establish that, maybe it's also not the best solution in the world. If we cannot establish that, it's always doing something. So that's the first point that we want to do in cooperation with the team that we have, just to validate first of all what we have.
Does it mean that, my last question, does it mean that I think at this moment, are you able to recommend us in which kind of patient we have to perform PFO?
I'm not a surgeon. I think that would be a little bit, I will take a lot of risk doing that. But for what I saw, also for what I studied and for what I analyzed, I would say value deformity controllable, not more than, in the studies that I read as well, definitely no more than 10 degrees of value deformation, and 10 degrees is already a exactly less than 10 degrees of value deformation, and when there is no other anomalies in the knee joint. Maybe the inflammation is big, or maybe it already has no function, and there are so many studies that they actually recommend when always mild value deformity, femoral deformities are kind of okay, and then they apply this. But I will take that much risk to saying you, yeah, do that, yeah.
Which is the future of these kind of surgeries? We will have to sit down together before we perform a surgery and to analyze all the data, and all the data that you need, you will recommend, okay, in this case, probably with this deformity at this age, with this sex, with this body mass index, with this probably is to perform a PFO, or this is the future. We have to work together in the hospital.
I don't think that's the future. Of course, collaboration is always good if we are there. But I think that's one of the things that we wanted to do as well with this study of the value deformities, that if we can deliver you some guidance, like, look, more than 5 degrees, femur angle more than this, the position of the fibula in relative to a normal plane, if it is more than this, And those are things that we can explore actually by doing in silico simulations. Of course, we only explore these, a few of them, like the varus valgus deformation, but we can as well explore after. Or maybe when the ankle position relative to the knee joint is different, I will avoid it because the forces behaves like this, like this. I think at the end, if we continue with this, we can give you as well a set of clinical support to say, yeah, the internist told me that if you have a knee, if you have an ankle relative degree of deformation to this, the forces are not that good at the end, or if you have this, actually looks good. I think at the end, we can give you kind of a guidance of these supposed clinical decisions at the end of the patient and of you as doctors, but we can say what we see. Maybe sometimes makes more sense. Yeah.
Thank you very much. Thank you. Again, I'm going to add my congratulations to you for a lot of work. Just going back to this, maybe a little bit of context. So it's just useful to explain that HTO used to be and I can be corrected by my surgical colleague, it was the treatment of choice before knee replacement was around.
Absolutely.
And so in terms of clinical data, we have more than 50 years of clinical data for HTO. And the survivorship of HTO actually is very good, really good. And there seems to be a relationship between the amount of correction and the outcome. So if you undercorrect, it is not good. So I think this is what plays a lot in the minds of surgeons who are considering this. It's seen as being challenging because you have to achieve the correction. And you aim for a correction or a slight overcorrection in order to get good clinical results. And if that's done, you get 20-year results where you have more than 80%. There are series with more than 90% survivorship at 20 years, which is pretty good. The unanswered question is how much do you correct? And there's all these different things that you do. And what kind of sits a little bit uneasily with me is that there's no calculation here. You just make a cut from the figure. And we have this experience from HDL that the amount of correction is really quite critical for medial compartment disease. And there are a lot of people tend to be in favor of medial opening wedge because you can control it a little bit more carefully, even though it introduces other kinds of challenges. But you leave the other part of the joint alone. As I understand, you're probably doing closing wedge if you're going on from the fibula. And there are advantages and disadvantages, but the vast majority of people. So maybe just talk to me a little bit about why this works. It just sits, it doesn't seem to fit with the data that we have.
Mm-hmm. One of the main aspects that we stumped in the beginning was definitely the amount of correction. It was already years ago, we say, okay, how can we analyze? Because this is definitely one of the most important factors at the end, correction of the angle, and we say, how can we measure this by using PFO in silico simulations? And we get our data, we got our clinical data, we got ideal models, we got models from database, and we start to play with the analysis of the correction of the angle. And we came to see, that's why I don't know if I can find the image here. It was not so easy in terms of boundary conditions, I would say, in order to simulate how PFO was going to react with the deformation. We really did a lot of things in order to get along the boundary conditions, in order to give us the best approximation to the deformation, to check the alignment correction. We defined as well within the Kulik's lines as a parameter. We wanted to check how was the deviation of the center of pressure in comparison with the Kulik's line with the mechanical anatomical axis. And unfortunately, it was not so easy as we thought, and at the end, it was not a variable that we could really use for us in a study as a reliable parameter, which was the alignment. That's why for the outlook, we really want to do, actually, we want to incorporate oscillator forces. We want to play with complex boundary conditions in order to allow the model to really have a bigger motions, and then after analyze the center of pressure location that we calculated. We did a job calculating this. And as you mentioned here, the overcorrection is a good factor. For example, for 2.5 degrees, it's actually overcorrected a little bit, which is as well in match that for my values, for I would say low deformation malalignments, it can just overcorrect, which is kind of good. But with this variable, we wanted to compare it along to the mechanical axis and the Mikulek slice to actually calculate this, how far away or how good it's actually reallocating not only the center of pressure, but as well the correction of the whole system. And it was not something that was pretty straightforward. So we wanted, for example, that's why actually it's part of the outlook. We know that this is one of optimization opportunity, I would say. But we know that it plays a role. Yeah.
It seems to me with this technique, you have no control as a surgeon, because you make the incision and you have no way to be able to say, this is the amount of correction I want to go. And it may be that if you stay within the 5 degrees, you don't operate any more than people with a deformity more than 5 degrees. That might be that. Just moving on a little bit, Jerome asked about indications to a certain extent. And in terms of osteoarthritis, it's progressive. We tend to use Kelvin and Lawrence grade. So grade 0 is normal knee, grade 4 is bone and bone contact. The problem with knee replacement is that it only really works if you've got end-stage disease, grade 4. And the nice thing about HDO is that you can operate at a much earlier stage of it. So there's a balance between age and grade of osteoarthritis. If you've got somebody very young with a very advanced disease, maybe you'll consider doing osteotomy. But what's the indication for this? Is it Kelvin and Lawrence grade 1 or 2? Or, presumably you wouldn't do this for end-stage disease.
Yeah, as well answered, I would presumably do it for early stage as well osteoarthritis, grade 1 or 2. I think the patients that we got, if I recall correct, they are as well 2 and 3 in all studies. We as well use the kid loans. Exactly. And I will use it for early stage osteoarthritis where really the varus deformation is still something I would say manageable for the mechanical system to remanage itself into position. I think if the mechanical system is already really deformed, it will be very difficult for the body itself to go again into position. Well, I would say indication early stage, mild osteoarthritis, varum, definitely. Yeah.
All right. So just going back a little bit in terms of anatomy. So I don't know whether you've been to a museum to see the dinosaurs. And if you look at bipedal dinosaurs, it's really interesting because their femurs have 2 separate articulations. They have an articulation with the tibia, and then they have an articulation with the fibula. So the bipedal, so like T-Rex, so the lateral condyle articulates completely with the fibula, and the medial condyle articulates with the tibia. And as we've evolved, when you look at mammals, I think there's been a change. And so, and we walk very differently to dinosaurs. So the dinosaurs are not very good at rotation. One of the thoughts about why we have this articulation completely with the tibia is about rotational control. So we can do something rotational with that bipedal dinosaurs. And probably having a tail can make a big difference to the way they deal with their rotational issues. So, is it that what's going on is not a correction in the function, but if you do this cut, that you're doing some things in the way that the rotational control works. That is a question. There's a lot of muscle attachments on the figure. I don't want to go too much into detail. I'll be interested in the surgical technique and the approach. And what they have to dissect to get that chunk of bone out. But there's a lot, I don't know if you've done any dissection, but there is a huge amount of muscle attachment on the fibula. And actually one of the nice reasons why people like doing medial open wedge osteotomy is there's not much there attached. You do a little bit of soft tissue dissection, but it's not, you're not really doing anything to the muscle.
So for rotation, as far as I could really see and analyze, I don't know if that has much influence into the rotational control of what we can do as humans. If we abstract the leg as a mechanical system in which the fibula takes part from the bottom system, and the forces are is a combination of the reaction forces to the ground and the forces and the weight-bearing forces from the upper side of the body. I'm not sure if the fibula plays the most significant role in control of the rotation. Probably there are some ligaments attached to the fibula, there is muscle around it, but if you disconnect it from the system, I don't know if it has the biggest influence in the rotation. I'm not sure if I can really answer that. Unfortunately, I don't have the anatomical study of the body as it is in order to see what's happening inside them. But if you disconnect from the mechanical system and there is not enough ligaments, muscles pulling or pushing energy from it or into it, I don't see if that really affects the rotation control.
I'm just going to jump to your characterization of the tissues. Maybe you can put the slide up where you looked at your different fits with the tensile test, not the DNA.
1 second like that.
Yeah. So just a comment really. When I look in a lot of the literature, I often see this type of plot where you've got strain and stress. And you've got 80% strain. I don't think physiologically you go anywhere near 80% strain.
Yeah.
Physiologically, you're probably not doing more than 10%, and you're probably not doing more than 5%. So the toe region is really quite important. And most of us, most of the physiological range of motion is within the toe region. And you've got a neo-Hookean fit, which seems to optimize better fitting towards the higher level of strength. So it's just a question about how you should better fit your neo-Hookean.
That's as well the question of why did we took some complex process in order to model it? Why we did actually the dynamic mechanical temperature analysis? We wanted to analyze as well. That was actually one question that we got as well from one of the reviewers when we submitted this paper. It's still under review. And it's like, when is actually as well happening that the tissue goes into 70 degrees Celsius? The knee is never physiologically going to that range of temperatures. It's something similar that the knee is never going to the same range of strength. I think in order to fit this better, we need to probably initial shield modulus to play it as well in between, and definitely increase the statistical data increases totally, and maybe a higher order hyperelastic material, more parameters. But yeah, I agree. I mean, in the larger part of the strains, it covers actually better, fits better in the toe.
Wouldn't it be better then you can optimize it by using a weighted fit, where you weight it down to the lower end of strength, which is more physiological, you'll get better.
That will be as well an option to fit to the part that we actually kind of interesting physiologically. But as I just mentioned, we wanted, first of all, we wanted to avoid not seeing something. That's why we did the whole range on the fold test. And after that, we can take optimizations methods. But first of all, we wanted to miss something out. That's why we did the temperatures in such a big range. Yeah.
Okay. Sure. Sorry, because that wasn't one of the questions I had. I didn't ask because of time. That's an important point. You should be aware that Newton models are valid maximum until 30% strength.
Mm-hmm.
The reason why is because it's based on the thermodynamic model of free energy. And this model of free energy has only valid until a certain relative movement of the polymer chains that are used to get this free energy. So if you try to fit Newton model by taking strain values that are beyond the range of validity of the model, so you're basically biasing the important information that Richie was mentioning, and the 10%. So it can be approximately as to be aware of.
I think that's as well a future thing to do as well, to take a look into the optimization of this material knowledge, definitely. I think there's improvement still to be done. But such input is very important, definitely. Thank you.
So, just leaving that aside, going back to the finite element issues, so just want to point out that I do a lot of finite element analysis. And one thing that was interesting to me in terms of the thesis, so you started off using ANSYS, or in the beginning of the chapters there's ANSYS.
Mm-hmm.
Then you moved to Abacus, is that right? Because you start using Dassault software, or did you stick with ANSYS as a solver?
We stick with ANSYS as a solver through the whole. We use CATIA for the modeling, SolidWorks for some modeling as well. A different set of software, we have Blender for some meshes and deformations. But we stick for the solver, we stick to ANSYS. Yeah.
So you're sticking with ANSYS, and then when you built these models using CT scans, so I've just got a question about how have you got the information about the menisci and the cartilage surfaces?
We got CT scans provided from medical partners, and we plot everything into materialize, mimic from materialize. We got this soft tissue, was not part of it. We got magnetic resonance from some studies. It was sometimes in not good shape, so at the end we decided to leave soft tissues modeling automatically from magnetic resonance out of the play. So we went together with our partner surgeons to model, I would say, manually, to model the soft tissues from the cartilage. From the femur was maybe not the most difficult. From the cartilage, medial cartilage, lateral cartilage, ligaments. That was a kind of a modeling task, definitely through the years. And together with the X-rays, and we modeled in basic literature, we modeled the soft tissues, most of them by hand, I would say.
And then it's useful to, when you're documenting in your thesis, so the thing that was really missing for me was a clear description of what's happening in terms of boundary conditions at the distal end, and also what's happening in terms of contact between the tibial and femoral surfaces. So could you just tell us what kind of contact conditions you use?
Yeah, contact from the femoral distal to the femoral cartilage was bonded contact. I assume that the femoral cartilage is bonded to the surface of the distal femur. And then from the femoral cartilage to the menisci and the cartilage and the top part of the cartilage and the top of the menisci was frictional contact with slippage 0.1 pinball millimeter radius to get the movement of the mesh into accordance. That was a contact, normal friction contact. And then from the distal part of the cartilage to the tibial plateau was as well again bonded contact, and in between femoral cartilage and tibial cartilage, friction contact, so normal contact. We did a lot of optimizations with non-Lagrangians and all the things that we could actually use in ANSYS to fit to converge, because it was a really difficult point as well, contacts. And then on the distal was remote displacements in order to allow translations and rotations from the anterior-posterior axis, and was all the other degrees of freedom was set to 0, to not allowed. And the remote displacement again in the femur, with allowance in order to go down into the Z direction and to rotate as well into the y-axis, I think that was. And as well from contacts, from the ligaments, we model contact ligaments when they got contact to the anatomical structure, I would say. We bonded them to the anatomical structures, and we use as well phase level linear springs in order to as well co-model the ligaments.
All the ligaments model the spring?
Spring elements are normal spring force and ratio, and as a solid models as well. So we use as well the material models of the ligaments.
Okay.
Static linear.
So that's two different approaches. So I just want to get clear. You didn't take into account the collaterals. Collaterals not considered.
The collaterals not considered, and we state as well in one of the chapters that we actually model as well influence of ligaments into the study, and the tendencies of the results were not changed. That's why we as well decided to not include them in some of the studies, but we as well analyzed the influence of them into the results, and it was minimal. Yeah.
You didn't model, so in terms of the frontal plane, there's no action of the ligaments.
No.
So you model the cruciate?
We model the crucial ligaments.
So the cruciate's in the middle, the collaterals on the outside.
Yeah. When we made the study of the influence of the ligaments, we modeled the crucials and the laterals, and we took a look what was happening if it had an influence in the result that we didn't get, and it was minimal. Minimal difference on the results that we were getting, so we decided to just not include them for further studies. But that was as well one of the main points of view to discuss when we got the paper published, what's happening with the ligaments. So we did a whole study again, so the influence with the ligaments, with what we were looking. That's why it was very important to define what we were looking out from the variables, and ligaments had no influence into what we were looking out. It was contact pressure and central pressure.
Because it'd be worthwhile explaining your contact in the model description, because it's not there. And in terms of the distal boundary condition, so did you set a displacement? Is it in Castor position at the bottom?
No, it was it's called remote displacement in ANSYS. I think in Abacus is as well the same. Remote displacement, it allows a set of surfaces, nodes, or elements to move depending on degrees of freedom. So I set 2 degrees of freedom from the distal. 1 degree of freedom, rotational.
So it can rotate.
It can rotate like this from the various values misalignment. Yeah.
Okay. But then there's no translational allowed.
There is no translation allowing it to simulate the contact to the floor or to the atom. Yeah.
Okay. And was that done for all the nodes on the bottom of the bones, or is it done for a single node?
It was done for the nodes and elements, for the nodes that I found with the X-rays to be more kind of in contact with the bones of the ankle. So it was maybe, I don't know, maybe 40% of the surfaces of the bottom surfaces, I would say, from the distal, from the fibula and from the tibia.
Okay. Can you just put up figure in 4.1.
Yeah.
And
Here somewhere.
that one.
Yeah.
So this is interesting to me because if I look at the femur to begin with, so femur has probably been the bone that's had the most finite element analysis done on it.
Yeah.
And what you generally tend to find when you load the femur in this kind of condition is that the medial aspect of the femur is put under compression. And yours doesn't show that.
You mean compression like higher stresses into this image? Or?
Yeah. And what you've got looks like the main kind of loading seems to be very much a sort of bending load put on the tibia. You've plotted hormesis. Do you know what, and you've got your other plots previously showing the contribution of compressive and tensile forces.
Yeah.
That if that looks like the tibia has been put into bending, and it seems to be very, I think it's driven mainly by your boundary condition. But I'm not seeing the normal bending pattern that I would expect in the femur.
How much is the loading expected? Because if we take a look to a lower scale, then we can see as well, of course, the force transmission is happening. The force transmission is definitely happening from the medial side of the femur in the distal part of the medial. So maybe when we plot this in a different scale, of course, it is happening as well. There's as well a big concentration of stresses here. I think it's as correct, but this is like bending moments and bending transfer forces, but I don't know.
So, what I found slightly difficult to understand. So here, when you look at the bending load that's being applied on the tibia, it looks like a classical bending load. But you'd expect, with that distribution of bending load, that you'd have compression where you've got your highest hormesis stress, the red. That would be compression. But you're saying when you plot it out against the different directions of load, that you're seeing tension on that side.
Now we can go to the next one. Roll is faster here. You mean in this one?
Yeah.
This is definitely in compression, as you just said. And that is what we expect from the medial side to be in compression.
Okay.
Yeah. The forces transmission.
It would be interesting to see what the influence of the boundary condition is. Because I think that is being driven by your boundary condition more than, I think your boundary condition has a lot of influence on it. So just for future work, I would suggest that you probably want to look at that boundary condition. The other question that, which you were able to solve some of these models in 12 minutes or so.
Yeah.
And that's with contact.
That's with contact.
And so the contact is always a bit of an issue.
Yeah.
And you use the quadratic element.
Yeah.
And so did you have to use a really, really small element size in the cartridge?
In cartridge, we use 1 millimeter element size. It was, of course, with a growing ratio. Depending on the curvature and proximity to edges, it could be reduced automatically. But the soft tissues were the most demanding, I would say. For the, we optimize a lot the meshing. And yeah, I think at the end the models were between 3 million elements to 5 million elements, and most of the elements were concentrated in the soft tissues. Sure. Yeah.
But if you look at, so in terms of your tibial and femoral cartilage thickness, so when you created those surfaces, you basically projected out the bone surface. And how many millimeters did you project those out to?
For example, for the femoral calculation, I think we use 2 millimeters or maybe 2 or 3 millimeters, depending. And for the cartilage, for the tibial cartilage, a little bit more, like almost up to 4 millimeters. Yeah.
Because one of the issues that I've always come across is that then if you've got an element size of 1 millimeter, you've only got 2 elements, which represent the thickness of the cartilage.
Yeah.
And then so you've got big difference in stiffness. So between the bone, the cortical bone and the cartilage, there's a big difference in terms of modulus. So when you start applying load, the problem becomes is the instability in the elements that represent the cartilage. And if you've only got 2 elements, you can get inversion of the elements. Just wondering how you dealt with that.
As I mentioned, we investigate a lot the element size, and that's why I use as well the Brogan ratio, and that's why as well we use proximity and curvature of the face in order to, when you get on top to the almost on the solid face, you were allowed, or the mesh was allowed to go smaller into element size. The same for the cortical mode. As you approximate to the outer solid face, the elements were allowed to be small, proximity and curvature. And convergency was in the beginning an issue, to be honest, and all was because of the contacts. I mean, we made a lot of simulations on this, so I performed a lot. That's why it was for me very important, this kind of guidelines, in order for me to follow myself again the same path, because otherwise I could struggle 3 years only with contact interaction and convergency. So at the end, had no stability issues about it, and even with contacts and.
So, and when you were meshing though, did you control for aspect ratio? That's the other
aspect ratio, ground ratio, totally, we control it, and as well dynamic meshing, because of the elasticity of the soft tissues, they could really deform themselves, so we go dynamic meshing depending on the loading. So.
Yeah. Were you meshing within ANSYS?
We did ANSYS, but it was.
You don't have a great deal of control in ANSYS over that, and that's the problem with curvature. Because if you're using text, because you can get a really adverse aspect ratio with the text, and especially if you specify a small size. And that's why, some people would argue that bricks are better. You can control the aspect ratio much easier, because when you've got curvature, you always suffer with smoothness. But yeah, I was really quite interested to see how you're able to get your solution times to 12 minutes.
Yeah, I think one of course computational power, one of the biggest roles.
But that really depends on how much you can linearize the model. If you distributed it. So I know you used GPUs and but the contact in particular doesn't lend itself well to being linearized.
At the beginning as I said, in the beginning I was really struggling. It took like 1 hour to compute something and then optimize the meshes, and then again 1 hour computing, and it was not convergent. I got no convergency, so it was really a huge deal, the whole convergency to bring it to a normal time.
What I would suggest though is that as a detail for your thesis, it will be very useful, because you went through all this process and there's no description as such of really particular technical issues. You might put it as an appendix, because if somebody else is going to come along and follow along, that's a really quite valuable, you can save them the problem if you explain some of this technical details, because it was just that level of detail, I think, is what I expected in some aspects.
I will take note, definitely. As a long journey, the whole simulation setup, and it was one eureka point of time in which look, now it's convergency, and then a lot of tests to validate the model again. And yeah, probably it could be added as well to an appendix if it's required. But it was a huge deal, and probably if someone is following along, maybe it can be useful. Yeah.
And then you picked 750 newtons as being the load that you apply to the femoral head.
Yeah.
What's the justification for that?
There's a lot of studies that use, depending on the patient-specific data, they customize them. For example, if the patient is 85 kilograms, they use 850 newtons. If they are 707 kilograms, 700 newtons. That's the most basic answer for a lot of studies based on patient data. What we do is we took as well, in the beginning of the whole research, we wanted to start as well following a baseline, and that was a paper that was as well simulating static simulations when applying PFO for just one patient. And they applied as well 750 newtons based on the patient data that we had. So we wanted to have a baseline to compare as well results. So we decided to follow as well along and to not have a numerical data that was comparable, or numerical results that were comparable. And after this, we had as well patient-specific data, like 80 plus minus 10 kilograms for the patients or something like that. But we decided to keep the data that we used in the beginning, or the force applied that we used in the beginning, in order to have to ensure consistency across all of our studies.
A lot of people that look at this kind of modeling, so the work from Bergman's group has been really useful because they've got measured in vivo load data, and taking a data point from that would be more physiologically appropriate.
Yeah.
And it's sort of self-justifying. You say this is the best data set that we have from being measured, because you're kind of neglecting quite a bit of muscle force if you're just taking the 750 newtons.
Yeah, that's a good thing. I will take a look as well. Yeah.
Because there's a large number of publications from that group, and they actually said they did the recommended loads for in vitro testing for implants, basically.
Yeah, I will.